exponential functions, we have that f of x is equal to a to the x power. This a represents a constant. It's a number. And my exponent is the variable. Since this exponent belongs to this number here, we call this constant, we also call it a base. Some books, you will see the exponential function written as b to the x. That is also valid, okay? A or b, they're both constants. And later on, we're going to talk about what numbers a and b can have. Okay, for now, anytime you have this function, we call this a parent function. This is the general form of the exponential function. If a is greater than 1, that means if this base is a number that is greater than 1, this is what the graph of that function will look like. Now notice how this graph shoots up very rapidly. Exponential functions grow very rapidly because the exponents are the variables. So imagine if I substitute x for 1, for 2, for 3, for 50, anything raised to the 50th power, that becomes a very large y value. So this line will be very, very, very high up here, very high value. So exponential functions grow very rapidly. Exponential functions are used a lot to represent bacterial growth, which is something that grows very quickly in nature. Bacterial growth, it's also used for population growth and also for money growth. You are going to see some examples and some applications using exponential functions for those fields. So we were saying whenever a is greater than 1, whenever this number is greater than 1, my exponential function is going to look like this. I'm going to give you an example of an exponential function. Let's say 2 to the x power. Okay, this is an example of an exponential function where a is equal to 2, or if you want to call it b, your base, and notice that it's greater than 1. So this function in particular will have a graph that looks very similar to this one that we have here. It will have a y-intercept at 0, 1. It will be above the x-axis. It's an increasing function. If I work from left to right, you notice that the values of y are increasing. We also call it a growth function. Okay, it's a growth when it's increasing like this. And notice that as my y value, as my x value is very large negatively, or as x is farther and farther away from 0 on the negative x-axis, my y value approaches the x-axis. And the x-axis is also known as the y equals 0 line. And this y equals 0 line we call also the horizontal asymptote of the exponential function. Why is it the horizontal asymptote? Because it approaches the x-axis, but it never touches or crosses it. So it limits my function. It tells me how low I can go with my y values. That's how low it goes. It doesn't get to have the value of y equals 0, this function, and it doesn't have any y negative values also. Okay, so this will happen for parent functions of exponential functions whose a value is greater than 1. When a is a value that's between 0 and 1, for example, if f of x is equal to 0.8 to the x power, for example, notice 0.8 is a positive number, but it is less than 1, I'm sorry. So it's between 0 and 1. Whenever you have a number between 0 and 1, it's positive, it's less than 1, then your exponential function is going to look like this. It's going to be decreasing, and we also call that decay. Okay, decay. So it's going to be very similar to this one, but it's going to be decreasing. And notice the y-intercept is still 0, 1. Your y-intercept will always be 0, 1 for a parent function in this form. Okay, later on we're going to see translations. The intercepts are not 0, 1 when we have translations. But when we have no translations, just the parent function as it is here, a number raised to an x power, then my y-intercept is always going to be 0, 1. And it makes sense because if I plug in a 0 here for x, 0.8 to the 0 power is going to be 1. Also here, if I plug in 0 for x, 2 to the 0 power is equal to 1. So that's why in both cases you'll have a y-intercept of 0, 1. Okay, this graph is also always above the x-axis. It has your y-intercept. It is decreasing, as we said, and notice that as x gets farther and farther away from 0 on the positive x-axis, the farther away I get from 0, or the larger my x value is, my function approaches the line y equal to 0, or it approaches the x-axis, which is also your horizontal asymptote. This means that no matter how big your x is, my y value will never be 0. Asymptote. Okay? So imagine an x, you have 0.8, and you raise 0.8 to the 100th power. And you can do this in your calculator. You will get a very, very, very small number. It's almost 0. Almost 0. That's why we say it approaches 0. So if I raise 0.8, let's say to the 100th power, I will get 2.03 times 10 to the negative 10 power. And you know that's a really, really small number. That's like 0.000000009 zeros, and then comes the 203. So it's almost 0. And that's what this means. The bigger this number, the closer your function will be to being the value of 0, but it never reaches that value. That's why we call it a horizontal asymptote. It's what we approach, but we don't touch, okay? Now let's talk about what a values are valid, okay? Remember, this is a number, a constant. We already saw what happens when this is greater than 1 and when it's between 0 and 1. We have here that it says that a cannot be negative, and it asks you why, and it's important that you know why. And I'm going to explain to you here. A cannot be negative. I'm going to give you 2 reasons. The first reason, let's say a is negative. Let's say negative 2 to the x power. A is negative. It can't be negative, but I'm going to show you why by having it negative. Let's say I want to graph this function. So what you do to graph it is you make a table with your x and your f of x, which is negative 2 to the x power, and we give values to the x and evaluate your function. So let's say x is 0. When x is 0, that means negative 2 to the 0 power, 1. When x is 1, that's negative 2 to the first power. That's negative 2. When x is 2, I get negative 2 to the second power, which is positive 4. When x is 3, I get negative 2 to the third power, which is negative 2 times negative 2 times negative 2, negative 8. When x is 4, I get negative 2 to the fourth power, which is positive 16. Look at what happens here to your y values. Remember, these are your coordinates, so you would be able to graph these on the coordinate plane, right? So I'm switching from positive to negative, positive, negative, positive. The next number will be negative, the next one will be positive, etc. If I try to draw that on a coordinate plane, that would be very, very erratical to have a function behave like that. For example, when it's 0, I get a dot here at 1. When it's 1, here's my 1 here. I get negative 2, so that's down here. When I have a 2, I get a positive 4. Let's say that's up here. When I have 3, I get a negative 8 all the way down here. When I'm at 4, I get a positive 16 all the way up there. Now, see how if I were to trace this, this becomes very erratical behavior, right? If this is what the curve looks like, I'm just joining points. This is very erratical behavior. This is not acceptable. Not acceptable, okay? So that's why a cannot be negative, because it doesn't behave well. The function doesn't behave well when an a is negative. Another reason it can't be negative is because x can also have, besides values like integers, positive and negative numbers, I can also have x have values like these. Okay, so let's suppose I have f of x equal to negative 2 to the 1/2 power. That I can change into a radical. And do we have a number that exists in our number system, in our real number system, which is the answer to the square root of negative 2? We don't. If it's f of x equal to negative 2 to the 1/4 power, that becomes the 4th root of negative 2, and we have the same problem. I don't have a number that when I multiply by that same number 4 times, I'm going to get negative 2, okay? So we cannot have even roots. Even roots, which are 2, 4, 6, 8, 10, etc., we cannot have negative numbers when we have even roots. Because whenever x becomes a half, this will be undefined in the real number system. That will be a hole in the graph. Whenever x is a 4th, I will get undefined again. So notice how this irradical behavior with just these numbers combined with when these numbers come up on my function, I will have holes. This just does not behave well when a is negative. So that's why a cannot be negative, okay? 2 reasons. A cannot be 0. Why can't a be 0? I'm going to explain it up here. A cannot be 0. There are also 2 reasons for this. Imagine f of x is equal to 0 to the x power. If I draw my little table here of values, if x is 1, this will be 0. If x is 2, this will be 0. If x is 3, 0, right? Because 0 to the first power, 0, 0 to the second power, 0 times 0, which is 0. 0 to the third power is 0 times 0 times 0, which is 0. And if I go on putting in numbers here, I will always get 0. So if I were to graph this function, I will have, for x equal to 1, I will have 0. For x equal to 2, I will have 0. For x equal to 3, I will have 0. And I end up with a constant function on the x-axis, or y equals 0 line. And this is not an exponential function. It becomes a constant function, so that's one reason why a cannot be 0, because it becomes a constant function. The other reason why a can't be 0 is because, let's suppose x is also 0. If x is 0, then this is indeterminate, and I'm going to show you why. 0, this would become, if I evaluate this for 0, this will become 0 to the 0 power, okay? And let's suppose I have 0 to the 5th power divided by 0 to the 5th power. My exponent laws say that this is equivalent to 0 to the 5 minus 5 power, which is 0 to the 0 power, okay? So if I think about where this comes from, and I think about this quotient, the first error here is I can't divide anything by 0 because that becomes undefined. Okay, so 0 over 0 is even worse. It's indeterminate, not undefined. It's indeterminate. I can't tell you what that is. And let me show you what I mean. When I say 12 divided by 3, that becomes 4. And we've always heard since grade school that multiplying and division are inverse operations. When you multiply, you can undo multiplication by dividing. When you divide, you undo dividing by multiplying, okay? So if 12 divided by 3 is 4, that means that 3 times 4 equals 12. That's what I mean, okay? Now look at what happens when I have, let's say 12 divided by 0. I would have to know that 0 times this answer is equal to 12. So I ask you, 0 times what is equal to 12? Nothing times 0 will equal 12. That's why this is undefined. Whenever we have a division by 0, it is undefined. But look at what happens when I have 0 over 0. When I have 0 over 0, I would have to ask 0 times what times this answer is equal to 0. And then you can say, well, 0 times 1 is 0. 0 times 2 is 0. 0 times negative 3 is 0. 0 times 5,000 is 0. A lot of possible answers. That's what happens when you have 0 over 0. There are a lot of possible answers. So that's when we say this is not undefined, but indeterminate. We can't determine what that will be, okay? So 2 problems when you have a equal to 0. One of them is when x is any number other than 0, you'll get a constant function. So it's not an exponential function anymore. And the other problem is when x is 0, that this is an indeterminate value, okay? We don't know what that will be. And our last restriction here is a cannot be 1. A cannot be 1 for the same reason it can't be 0. If I have f of x equal to 1 to the x power, if a is equal to 1, look at what happens when I draw my table of values here. If x is 0, y is 1. If x is 1, 1 to the 1 power, 1. If x is 2, 1 to the second power will be 1 times 1, 1. If x is 3, 1 to the third power is 1 times 1 times 1, which is 1. Okay, if x is negative 2, for example, that will give you 1 to the negative 2 power, which is the same thing as 1 over 1 to the second power, which is 1 over 1, which is 1. You still get 1. So any value you choose as your x will give you a value of 1 for your function, and that becomes a constant function at y equal to 1. And I'm going to draw that up here since I ran out of room. Let's say I want to draw that 1 to the x power. Here's what you'll have when x is 1, y is 1. When x is 2, y is 1. When x is 3, y is 1. When x is negative 1, y is 1. When it's negative 2. So you'll get a constant function at y equal to 1, and this is not an exponential function. So that's why a cannot be 1 or 0, because in both cases you will get a constant function. And additionally, when it's 0, remember this problem here, the indeterminate form. So it can't be 0 because it becomes a constant function, and also indeterminate for x equal to 0. It can't be 1 because it becomes a constant function. Now we're going to talk about translations. You've seen translations when we saw the other parent functions, the quadratic function, the absolute value function, the x cubed function, the square root function. We worked with translations. So they're basically the same. Okay, here's my parent function. For this example, I'm going to use the parent function 2 to the x power. Notice 2 is greater than 1, so this is increasing. It is above the x-axis. The y-intercept is 1, 0, 1. Okay, and now I have this function here, which is the parent function with a slight change. It has a change at the x. So this means that this change will affect my x-axis because it's changing the x. It's adding 5 units to the x, okay? So whenever I see a plus 5 with the x, that means I'm going to have a shift horizontally. It's either going to move to the right or to the left. How do I know? Well, if it's plus 5, it moves to the left. If it has a plus, it moves to the left. If it were minus, like over here, it moves to the right. How many units? The number that it says here. It's going to move 5 units to the right. And what does that mean? Well, it's easier for this function to look at the y-intercept. The y-intercept will move 5 units to the right, okay? And this graph, if you notice, here are the values for my x-axis. They're increasing in numbers of 2. This is 2, this is 4, this is 6, okay? So here's my y-intercept. I'm going to move it 5 to the left. Here's 2, 4, 5. There's the new there's the new place for your y-intercept. It's not a y-intercept anymore though, okay? It was the y-intercept for my parent function, but for this function, which is a translated function, this point moves 5 units. And then you can sketch your graph, okay, including that point. Your horizontal asymptote also moved 5 units to the left, but it's still your y equals 0 line, okay? It only moved like this. It shifted, but it's still the value y equals 0, okay? For this case, I moved 8 units. So if this is the y-intercept, this is what happened. 2, 4, 6, 8. See? It moved 8 to the right. And your horizontal asymptote also moved 8 units to the right, but it remains at the y equals 0 line. Okay, so your horizontal asymptote, notice, is the same as your parent function. Okay? Here we have vertical translations, which mean moving up or down along the y-axis. Okay, so here's my parent function again. And here, whenever you have a +4 outside of the function, that means it's not altering your exponent like the one we saw before. It's outside of the function. That means I move up or down. And in this case, when it says plus, I move up. What moves up? My y-intercept will move up 4 units. And notice here on my y values, these are increasing by 1. So if my y-intercept is here and I'm going to move up 4, I'm going to go 1, 2, 3, 4. There it is. Okay? And in this case, your y-intercept remains the same as the y-intercept in your parent function. And then what changes? Since you moved, it's like grabbing your horizontal asymptote, which is y equal to 0. It's like grabbing it and moving the whole thing up 4 units. So notice how your horizontal asymptote is now up here for your translated function. Okay, so imagine grabbing this whole section here of your parent function, grabbing that and pulling it up 4 units. Your horizontal asymptote will also go up 4 units. 1, 2, 3, 4. And there it is. Okay? Notice the horizontal asymptote is just an imaginary line that lets you know your limits. Okay? Now, when I have -3, that means I go down. How many units? 3 units. Now, let's see here. Here's my parent function. Here's my y-intercept. I'm going to move that y-intercept and my horizontal asymptote, which is at y equals 0. I'm going to move that whole thing together, 3 units. So if I move my y-intercept 3 units down, this is where I'll be. 1, 2, 3. Good. If I move my horizontal asymptote 3 units down, this whole line, I'm going to move 1, 2, 3. And here is the new horizontal asymptote. Okay? And you can see that it fits. My new function, which is translated 3 units down, approaches my new horizontal asymptote. Okay? Horizontal and vertical stretches. Here's my parent function, 2 to the x. That's the red function. Horizontal stretch. That's like picking up this x-axis by both sides. Okay, if it were possible, and pulling outwards. It's like pulling the x-axis outwards. That makes a horizontal stretch. Okay, and here's what that looks like. Here's an example. 2 to the 0.8x power, 2 to the 0.4x power. Whenever your exponent is multiplied by a number that is less than 1, but positive, okay, you're going to have a horizontal stretch. So notice how this blue one, which is 0.4, it's stretched out to the sides. And so is this one, not as much as this one. The closer I am to having this equal to 1, the less stretching, okay? For this one, this is a vertical stretch. So the vertical stretch is like grabbing the y-axis and pulling it upwards or stretching it upwards, and the graph will stretch upwards along with that pulling. So here's my parent function, the red one, and here I have the blue one. Look at what happened. I'm multiplying 3 times the whole thing, the whole function. So after I've evaluated 2 to the x power, after that value, then I multiply by 3. So my y value is going to become bigger. Okay, so this function will grow more rapidly because I'm multiplying by 3. That's a vertical stretch, and that happens anytime you multiply the function by a value of y, okay? I mean by a number here that's greater than 1. It's gonna stretch. Okay, here's the example with a 5. Notice how 5 grows even more quickly than when I multiply by 3. Okay? And here we have our reflections. Whenever you have a negative in front of your exponent, this is affecting your x. Anything that affects your x negatively, like this one, will be shown on the graph as a reflection across this axis, the y-axis. How do you visualize this? Well, imagine this is a piece of paper and you want it folded in half along this line. If you fold it in half along this line, then how do you say, and you were to trace this line, this parent function, if you trace this, if you fold it across this line and you trace the line, this is what you'll have. Okay, you'll have a reflection of the line. And notice that this reflection across the x-axis maintains, this is the parent function, of course, you keep your y-intercept, and your horizontal asymptote doesn't change, okay? When your negative value is outside of the function, not affecting x, then it's going to reflect across the x-axis, okay? When I said here it affects your x, I mean that your positive x values are now negative x values, because that's what it says, is the opposite of x. So if my parent function with the positive x values, now I'll have negative x values. So that's why this becomes a reflection. Here, my positive y values are now negative y values. That's why my y values here that were positive are now negative y values. And very important here, this is a parent function. Here's your horizontal asymptote. Okay, notice that this is reflecting across the x-axis. I can also say it reflects across the horizontal asymptote. Later on, when we see translated functions, we're going to see that instead of saying reflection across the x-axis, it's going to reflect across your horizontal asymptote wherever it is at that moment. Okay, we'll see that in the examples when we're sketching. Okay, and this is it for exponential functions. It's basic knowledge, how to translate them up, down, left, right, reflect them. On our next video, we're going to see some applications of exponential functions. We're also going to see the natural number e, and I'm going to give you some examples on sketching. I'll see you in the next videos.